Hi everyone, my name is Nick Dutton, and I'll be talking about a heuristic algorithm that we've developed to help identify thin curved lines in the presence of noise with structure, and how we use this algorithm on bistatic radar waterfall plots with great results. As for an agenda, we'll first go through some background information and problem definition. We'll talk about why what we're doing is hard, then we'll provide some updates to the previous approach that we presented at the Planetary Data Workshop in 2019, and finally talk about the new results. We use this algorithm to find the direct path in bistatic radar waterfall plots derived from data produced by the MiniRF instrument aboard the Lunar Reconnaissance Orbiter, or LRO. Bistatic radar just means that the transmitter and receiver are physically separated. In our case, we transmit from Earth in X or S band and receive at LRO, which is orbiting the Moon. The direct path is the signal received directly from the transmitter. It shows up as a sparse thin curved line in the radar waterfall plots. There are also other signals present in the radar waterfall plots, such as backscatter or diffuse reflection, and forward scatter, which is the specular reflection of the signal. Our previous approach in finding the direct path occasionally required a human in the loop, but now we're able to find and fit it for every collect that we've taken. So this figure on the left is an example of a waterfall plot. We see the three primary signals that show up as the direct path, forward scatter, and backscatter. Each row here represents a received pulse, and each column represents the radar's sample of that pulse. So why do we want to define the direct path? Well, the direct path allows us to treat the bistatic radar like a monostatic one. If we know the timing and phase of the transmitted signal at the spacecraft, we can then model the transmitted chirp state at the spacecraft. This job of finding and fitting the direct path is actually pretty challenging. 5 examples are highlighted here to show how different issues can crop up. Going from left to right, the direct path can cross the forward scatter and or backscatter, causing the signal to be difficult to pull out in those regions. Sometimes there are additional noise sources that crop up and follow the signal. We have a few collects where we're missing data, but we still need to find and fit the direct path so that we can form an image in those regions where there is good data. The direct path normally isn't the strongest signal with X-band data and can actually be quite weak. And lastly, sometimes the forward scatter is very thin, so distinguishing it from the direct path can actually be difficult from a computer's perspective. The one on the far right actually failed on our last version of the algorithm. This slide is a summary of the primary updates to the algorithm from the previous version presented at the Planetary Data Workshop in 2019. We'll go through each of these steps and show an example for each. The first key feature update increases the signal density of the direct path by combining both the linear receive horizontal and vertical, or H&V, channel data during pulse compression. MiniRF receives in 2 polarizations, H and V, so why not combine the two and improve the data quality? The previous version of the algorithm only used the horizontal channel data for pulse compression. The figure on the left shows the algorithm with just the H channel, and the figure on the right combines both. We can see that the number of data points that make up the direct path estimate has increased, which will result in an improved fit for the direct path location. Next, we pulse compress the data, then compute the sharpest peak for each row or pulse in the waterfall plot. We use the fast Fourier transform of the peak locations to determine if the amount of drift per pulse is under some threshold in order to make the direct path nearly vertical. Once we're done iterating, we now use the mode of the sample estimates to compute the single best guess for where the direct path is. Here's a review of the sharpest peak algorithm. We basically just loop through each sample and compute an average window intensity on each side of that sample, store the difference between the windowed average and the sample in question, and then the one with the highest ratio is the sharpest peak. This technique is important because it selects the sharpest peak, not necessarily the most intense overall. These figures show 2 iterations of the pulse compression process. The red X's are the sharpest peak estimate. As you can see, the data is quite noisy, but you can still make out some structure here, like the forward scatter, the back scatter, and the direct path. The green circle is the mode of the estimates in terms of samples. It gives us the sample in which the direct path estimates occurred most often. We can see that by the second iteration, the direct path is fairly linear, and the mode has selected a good location. Next, we want to provide estimates along the direct path and attempt to remove some of the noise estimates that we just showed. We apply a boxcar filtering approach where we sum columns inside the box encompassing the direct path mode. We then again use the sharpest peak algorithm within the box and slide that down to sample the full direct path. Finally, once we have those estimates, we apply an initial filter that rejects estimates that are not locally linear. Up to this point, we've just shown how to get estimates for the direct path's location within the waterfall plot. At this stage, if there is similarly shaped noise near the direct path, we can have remaining points in our estimate that will mess up our fit for identifying the signal. We've come up with a way to mitigate that with a custom filtering approach. Let's walk through an example. The direct path is in the center and curves sharply up and to the left. After our boxcar approach, we see that we have some remaining estimates that we don't want in the upper right, where the forward scatter is very close to the direct path. After we apply the initial filter, where we assume things were nearly linear locally, we still have some remaining points. These points have structure, as you can see in the yellow ellipse. These points can't be categorized as outliers since they have structure. Outlier rejection techniques such as the Hampel filter will not work well in this situation. We also can't simply accept estimates where the noise is minimal on either side due to the high variability in the background. It just doesn't work. So what do? We want to maximize the data we have available for fitting. Otherwise, some regions could become sparse and the fit could be poor. We also don't want to include any data in the problematic region, so what do? First, we categorize a segment as a series of direct path estimates between jump discontinuities. There are 5 segments in this example, shown by the colored ellipses. For each of those segments, generate all combinations of the data within those segments, assuming that the largest data series is always present. That would be the black ellipse in this particular example. This results in 2 to the n minus 1 combinations. Next, for each of those combinations, we fit a low-order polynomial to the data and store the residuals for that fit. We use a second-order polynomial for the direct path. The maximum ratio of the number of segments to the residual fit error across those combinations is the combination that maximizes our data available and also best approximates our signal. Here we see the filter works very well. It removes the incorrect estimates and also kept the maximum amount of data we had available for the fit. We can then fit the data contained within the selected combinations of segments to a higher order polynomial and reference it as the direct path going forward. We have about 120 total collects, and now they're all fully automated with no need for a human in the loop to select it. Or said in another way, for any Star Trek fans out there, the Ferengi Rules of Acquisition Rule 242 states that more is good, all is better.